Thank you very much for staying until the last session. I know there is a dinner coming up, so I won't hold you for too long. I think there's one more session that you'll have to stay. The plan of this talk is to first tell you a little bit about Cosmic Explorer. I hope to get through that in 5 minutes. And in the second part, to tell you about the science that is enabled by Cosmic Explorer together with other ground-based gravitational wave observatories that we hope will be operating at the same time. I will start with where Christopher Berry yesterday stopped, showing what he expects the timeline to be. Over the next few years, we hope to have observations by LIGO and Virgo principally, but with Kagra joining best case effort. We may have to wait until 2025, 2026 for an improved sensitivity that's useful for joint observation of Kagra. But LIGO and Virgo are on the path to making remarkable observations, increasing significantly the number of observations that they will make. As you have heard throughout this meeting and at other places, we have not only impacted our current understanding of fundamental physics, astrophysics, and cosmology with these observations, but at the same time, these have raised a lot of new questions as well. I have put the questions that I recognize are important right after my summary slide, and if somebody would like to take a look at that, the slides will be available. But I want to just focus on what comes after the LIGO, Virgo, and Kagra. In fact, both the LIGO and Virgo collaborations have started planning improvements even beyond 05 to have detectors with even slightly more improved capabilities. It's not something that's concrete. I won't touch upon that, but an effort to go beyond even those sensitivities began a few years ago, and the next generation observatories, and not all of them are next generation, because as you can see, some of them have already started making detections here on the lower left corner, or at least tantalizing hints towards detection. So we observe space observatories and pulsar timing arrays to vastly increase the bandwidth of observation. And at least for some of the sources that we will observe from space, Lisa, the ground-based observatories will observe them together. And this multi-band observation is sometimes very useful, as might be stressed in some of the talks. I think some of the talks are going to talk about multi-band observations. So with upgrades of advanced detectors, A+ Kagra, and with the new LIGO India detector joining, and an improvement over LIGO, a concept called Voyager, we might have reached the final sensitivities that are possible with existing facilities. And beyond that, we are essentially talking about new detectors, NEMO, which stands for Neutron Star Extreme Matter Observatory, a concept in Australia, Einstein Telescope, a European concept, and Cosmic Explorer. These are beyond 2035. There are new ideas which are still mostly ideas, except the LIGO, which has made a lot of good progress. And then in the low frequency and ultra low frequency, which I won't touch upon. This talk will mostly talk about, we'll be talking about ground-based observatories, specifically Cosmic Explorer. So what's Cosmic Explorer? It's a next generation gravitational wave observatory, and maybe 2 sites. It's based on the current LIGO concepts, except they are going to be 10 meters longer, and therefore 10 times longer, and therefore 10 times more sensitive. After an exploratory study, a horizon study that I will mention in the next slide, we came to the conclusion that the best signs can be returned by two L-shaped sites, one with 20-kilometer arms and another 40-kilometer arms. I won't touch upon why that is the case unless we want to go into that during the question time. These observatories will be built, or they require large lands, and these are indigenous lands, and there's considerable effort that has gone into planning how to accomplish community engagement and involvement in the project right from the beginning. The observatories are meant to be about 50 years lifetime, housing a progression of detectors. We don't think that the sensitivities that we are currently thinking is the end game. There may be new possibilities, and the scope should allow such improvements in detector subsystems as we go along. It's likely to fully explore gravitational wave observation capability in this acoustic band. What we mean by that is that it has the potential to observe the classes of sources that we currently think exist, but Cosmic Explorer itself might uncover things that nobody envisaged. We don't know the cost really very well, but it is likely to be on the order of $2 billion. And the time scale, as I indicated, is something like 2035. The science goal is what we're going to talk about, and I won't spend too much of time here. The team that was involved in the Horizon study funded by NSF is given here in these logos. It consists of 5 universities across the US, $3 million involving of order 5 postdocs and 10 students in these universities. We had also help from scientists and engineers in LIGO lab, especially consultants for civil and vacuum engineering. We are moving on from this Horizon study now to a project structure, a collaborative effort involving now of order 10 to 20 universities. We are currently populating the various project tasks with volunteers at the current time. There is no money for any effort at this time, but we are going to be writing a proposal for the conceptual design phase, which we hope the right vehicle is MREFC. The external to the project is the Cosmic Explorer Consortium, which we already formed at the time of the Horizon study. Anyone is welcome to join. CosmicExplorer.org tells you what you need to do to join. There's really not anything much other than signing up to your mailing list. Currently, there are about 378 scientists that are part of the CE Consortium. Apart from other activities, we have monthly consortium science calls that may be of interest to the group here. It is led by Salvo Vitale, and there are R&D calls led by Lisa Basotti. The next consortium call is actually 25th of May. I should have put the date there, and I'll correct it later. Okay, what the Horizon study led to is this document, a Horizon study for Cosmic Explorer, science, observatories, and communities. The goal of the Horizon study was to identify the science priorities of different funding agencies, and we systematically went through various different agencies within the US as well as international. We selected some subset of science goals that are accessible to gravitational wave observations, especially focusing on those questions that are uniquely addressed by gravitational wave band and multi-messenger astronomy. We then had a study in which we wanted to connect science goals to design choices, the number of detectors, the detector location, the length and configuration and so on, and availability of other detectors at the same time, such as the second generation detectors that might still be operating and Einstein telescope. This resulted in a trade study with something like 450 plus detector networks, and the main results is contained in this CEHS document, but I'm going to talk about some of the detailed results drawn from this paper a student of mine led. We had a pretty good endorsement of Cosmic Explorer in the Astro 2020. Just to quote, it says, gravitational wave astrophysics is one of the most exciting frontiers in science, and planning the next generation observatories such as Cosmic Explorer is essential. The survey committee strongly endorses gravitational wave observations as central to many crucial science objectives. So this is, we are now working on this conceptual design study, which will be 2022-2025. Sorry, that is not part of the recommendation. I should really change that. I'll do so later on. It should be the next bullet. So the preliminary design with NSB blessing, we are hoping will be on the time scale of 2025 or 2028, with construction starting at 2030. Yes. And that construction is about 4 years, and the commissioning and first flight around 2035, if all goes according to plan. This is a rough timeline. I won't spend much time. It's roughly what I've been talking about. Site is selected in the next about 4 to 5 years. And then we are hoping for funding around 2028 and the construction beginning in 2030. And you can see, the first lock or first light around 2035. So now I will just mention one word about Einstein telescope. This has been selected by S3 roadmap, and that is a signature of community endorsement. They are moving on to site selection now, but more recently, the Dutch government committed significant funding to R&D, 42 million euros, and also installation money provided. Einstein telescope gets installed in the in Netherlands. This is from National Growth Fund, and they are reserving 870 million euros, almost €1 billion for future Dutch contribution to the construction. But if you require, if you read the document, it says conditionally to indicate that if the detector gets built in the Limburg region. So the next 10-15 minutes, I want to spend time talking about the capabilities of next generation detector networks. As this science wheel shows, there are three main themes that we would like to accomplish, and these are the science goals that are drawn from the various funding agencies, their science priorities. On the one hand, extreme gravity and fundamental physics, which will look at unusual compact objects, the nature of general relativity and gravity, and the existence of dark matter, whether it is in the form of particles or waves. And secondly, black holes and neutron stars throughout the cosmic time. They could be black holes forming at the very early universe, and that might seed the galaxy formation itself. And what are the populations of compact objects throughout the universe? We can explore that. And the third theme is dynamics of dense matter. These are neutron stars, and we don't understand the structure and the composition of neutron star cores, and gravitational wave observations will allow to explore that. What we shouldn't forget is that a detector like this, with a reach that goes from the local universe to all the way to the edge of the universe, which astronomy has typically taken several hundred years to accomplish, is possible because of the way the cost grows with the length rather than the area of the interferometer. And that's the reason why we are able to make that very big step within just about 40 years or so. And that is what is, is possible for this left-hand diagram, where you can see how far we are able to see stellar mass black holes all the way to the beginnings of star formation in the universe. I'll say a little bit more about that as we go on. The next about 5 or 10 slides are drawn from this work that a student of mine did as part of the trade study. The most important question that we want to understand is the population of binary neutron stars and black holes. And what is important in this context is how far can you see them, or the completeness of the survey that Cosmic Explorer can do. And typically one takes about 50% completeness level. And here we see that this whitish lines, which is the next generation observatories with Einstein telescope, Cosmic Explorer, and another version of Cosmic Explorer in Australia. This observatory goes almost to the edge of the star formation peak, which occurs around redshift of 2 or 3. We don't know exactly where. Even at that distance, it can observe 50% of all binary neutron star mergers. As you go to the inner plots, the round circles here, they are for redshift, sorry, signal to noise ratio of 10. These squares are for signal to noise ratio of 100. So even for 100, we can see up to 50% completeness up to redshift of something like 0.1, which is where many telescopes are able to make observations, and we are able to provide exquisite measurement capability even at that distance. Another related question is, how many sources are you able to detect? This plot shows you as a function of redshift, once again, the detection, so this is not detection efficiency. I think that plot should have gone back. I don't know why it didn't. So this is really the number of detections here. Yeah, the detection rate. Oh, that's black holes. Yeah, they should have been. Let me just try to fix this. Give me 1 second. Not clear why. Okay, I know what has happened, but I don't think it's possible to change that. But anyway, this is just the number of detections as a function of time. For different detectors. And what you see is that the total number is something like 500,000, 500,000 binary neutron star mergers per year, out of which you will be able to see 1/2 of that, 50% of that, with this ECS detector, whereas with the current generation, you are somewhere here in this A plus is somewhere here, which is maybe several hundreds per year is what will be accomplished by the A plus detector network. Moving on to binary black holes, here the reach of the detectors is truly impressive. What you see here is that even at redshift of something like 20, we are able to observe 50% of all binary black hole sources at that distance. And the number of detections here is at the level of 200,000 or so. That's the total number of sources that we will be able to observe binary black holes per year. And almost, all of them are accessible to the next generation detectors, whereas something like 1,000, the relevant number here for the A plus detectors is something like a few tens of thousands, about 1/10 of all the population. I'll give you some highlights because those graphs don't tell you the complete story. As a function of time here, how we are able to increase the reach of the detectors from the local redshift of simply 0.4 to something like redshift of 2.3 with the 50% completeness of the catalog. This is just the completeness of the catalog. And then if you ask what is the total number of detections, as I said already, something like 1/2 of all the population of binary neutron stars could be observed, whereas with the upcoming runs, it is at the level of a few tens. With A plus, it will be of the order of a few hundreds. And then, with improved sensitivity of next generation detectors, will be remarkable improvement of observing almost half the entire population in the universe. Not only will we observe most of these events, 50% of the events, but there'll be many with low signal to noise ratios. For instance, about a few hundred to several hundreds for the next generation detectors here is what is possible. And what can you do with that, when you have such loud events? And one example of this is measuring the neutron star equation of state. The radius and mass curve is what is one of the ways in which we can infer the equation of state. And there are 3 different equations of state here. And the current universal relations have certain problems with them. But if you can correct for those biases, systematic biases, you will be able to measure the neutron star mass radius curve, and hence the neutron star equation of state extremely accurately. The yellow points are the ones that are finally relevant here. The blue points are the ones that are uncorrected, but when you correct almost all the points, you get very close to the real equation of state. If you don't correct for it, then there are biases, and those are the kind of things that one could do. And this way, you will be able to measure the radius of the neutron star to sub 100-meter level if there are no other systematic errors. Of course, these are the kind of things that we need to do now to identify what are the requirements from the waveforms, accuracy, what are the systematic uncertainties that might come from calibration, and so on and so forth. So those are the kind of things that we need to do as we go along. Moving on to binary black hole mergers. Here we can see binary black hole mergers with next generation detectors pretty much, before the first stars, the population 3 stars form with next generation detectors. Whereas with the current facilities, you can really only reach what I call local universe. These are by no means local. This is redshift of 1.4. But with next generation detectors, there's a massive leap in what we are able to accomplish. The story is similar for the number of events. In this case, you will be able to detect all the events that are available to you. But not only that, we can observe loud events with large numbers, 18,000 here for binary black holes, 8,500 here for next, what I call one third generation detector together with A plus sensitivity, NG plus. Not only that, we will observe several tens of super loud events with signal to noise ratios of greater than 1,000. Those are the kind of things that are needed in order to do precision tests of generativity and so on. But observing the numbers is not the only thing that is important. We need to understand how well can we measure things like localization and the distance measurement. And this plot shows you for a 10-year population of binary neutron stars, how well we can localize sources as a function of redshift. So the x-axis is redshift, the y-axis is the signal to noise ratio. The nearby sources here with the next generation detectors can be, that's binary black holes. These binary neutron stars can be really exquisitely localized. The dark purple here is omega 90% credible area of between 0.1 to 1. This one here is 0.01 to 0.1. And the final one is between 0 to 0.01. This final 0.01 we chose in order to say how we might be able to localize a single host galaxy within 300 to 500 megaparsec associated with a merger event. So this can be remarkably done with binary neutron stars, several tens of them every year to several hundreds of them over a period of 10 years, of course.
Sathy, you have 5 minutes left.
Got it. Yeah, I'm keeping a watch. And a similar thing can be done with dark sirens, that is binary black holes. We will be able to localize them to very good precision and identify the host galaxy, and therefore use even dark sirens for cosmology. As you can see in the nearby universe, if you can identify them within redshift of 0.1 to 1, which is what this purple plot is. And you can go even to redshifts of several, but that might not be useful. There, I think galaxy clusters are still possible to identify and associate. That subset will still be useful. Maybe 5% of all the events can be localized to single galaxy clusters, and that is still useful. But we will have a significant population that can be localized to single galaxies in the local universe, up to 300 to 500 megaparsec. I think I'm going to skip this 3D localization. We can measure not only omega 90 that I was showing. These are for different detectors once again, but I'm going to skip this because Shinyu is going to talk a little bit about cosmology in the next talk. Here are some numbers. The left one is for all the sources that we can observe, and the right one is for sources within redshift of 0.5. How well we can measure the position on the sky, that's omega 90, and the distance to those sources. As you can see, this is even for all the entire population, this is a very impressive numbers, and this is what allows for us to do follow-up multi-messenger astronomy, but also cosmology with gravitational wave sources and gamma ray bursts and so on. I won't have time to touch upon those. Not only that, we should be able to say that an event is coming within 2 minutes or 5 minutes or 10 minutes, depending on how loud the event is. Let me just go back to that for a minute. And we can do so for several thousands of events in the case of 2 minutes, and that is enough for many telescopes to follow up. But some telescopes might require a little bit of trigger time, and that could also be done, and to very good localization as well. With a 10-year observing run, we might be able to identify binary black holes with signal-to-noise ratios just in the post-merger of several thousands. These will, several hundreds, I'm sorry. Several hundred events with the signal-to-noise ratio greater than several hundred, and they will allow us to do precision tests of things like quasi-normal modes. We will be able to identify the origin of binary black holes, whether they are in the beyond the first formation of stars. For instance, this very nice work by Ning et al. Shows you how even a single observation will identify the origin of these binary black holes to beyond redshift of 20, within a redshift of about 5 or so, 20 plus or minus 5. We can detect sources even all the way up to redshift of 100, but pinning down their redshifts purely from gravitational wave observations will be difficult for even higher redshift. But I think we can conclusively say whether a population exists beyond a redshift of 30, which is really the limit when population 3 black holes can form. Another example of what we can do is really discover early universe phase transitions, including beyond standard model predictions such as supersymmetric phase transitions, and ask related questions in fundamental physics. Let me just quickly conclude that there are many opportunities for discovering new physics. This is a SNOMAS paper written by Brito et al., where they talk about all sorts of dark objects, and both of wave nature and particle nature, that could be detected by gravitational wave observations. And here is an example, but I think I'm running out of time to talk about imploding neutron stars that can be detected. So I will reserve that for any question time. Let me also point out another SNOMAS paper where the authors have identified how next generation detectors allow us to test general relativity to very high precision by many different methods, not only production of gravitational waves, but also their propagation over cosmological distances. With that, let me stop here. I think I've run out of time. Let me put this summary slide and take any questions. Thank you.
Great. Thanks very much, Satya. Questions for Satya? So I had one quick clarification. You had NG plus, which was clearly the next generation, and then ECS. Is that Einstein Telescope and Cosmic Explorer? What are those? What were those acronyms for?
That's right. I didn't spend too much of time. Oh, sorry. That's not what I wanted to share. I think I want to share the slides. I didn't spend much time talking about the different things. I'll just go back because this is question time now. Here. As you can see, there are these 6 different detector networks. ECS is for 3G detectors. Einstein Telescope, Cosmic Explorer in the US, only 1, and Cosmic Explorer South in Australia. But you can imagine that 3rd detector to be somewhere in the US as well. This is not going to change too much. There may be some degradation in the numbers for sky localization, but it's not going to degrade the quality of science that you can do. I mean, almost all the plots, follow those things.
Yeah.
VKI stands for the Voyager Virgo, Kagra, and LIGO India, plus 1 Cosmic Explorer. Here, 1 Einstein Telescope, and so on.
Got it. Thank you.
So I have a question about the primordial black holes detection from the future experiment from the Cosmic Explorer, for example. Before the first stars, essentially there are no collapsed halos for baryons. So what type of electromagnetic counterpart will be needed for determining the redshift in the case of primordial black holes?
Oh, this is not redshift from electromagnetic observations. What we are plotting here is the redshift inferred from the distance. You assume a cosmology.
Okay.
You convert the gravitational wave measurement distance to redshift.
It's assumed then. Okay. Thank you.
Yeah. Hopefully, nearby observations can fix the cosmology for us, and that will be valid all the way up to redshifts of several tens. That's the hope.
Yeah. Thanks, Satya, for the talk. Could you give us a sense of what are the technological challenges you expect in scaling up the detector by a factor of 10? Is it just the same, detector that exists today scaled up, or are there some new developments?
There will be new developments, or rather new developments required. You cannot just hope to have the same mirrors. The moment you would make the detector longer, obviously there's going to be dispersion, and hence you would need to build bigger mirrors. You need larger powers to be maintained. It's not clear whether the current coating technology will be sufficient to do that. We are already reaching those limits, and therefore you need new substrates. And it may be necessary to cryogenically cool. That's not in the design currently, but that's an option that one can use in order to reach the final design. So there are going to be new R&D required, but these are not, while these are interesting and technologically challenging, they are not unreachable. They are, in a way, it is a scaled up version, but it doesn't mean that there won't be any challenge at all. But it is doable.
Thanks. Yeah, question here.
So I was wondering, like a long-standing issue in astrophysics has been the initial mass function of the population 3 stars, so the distribution of masses. And to what extent would you say that these next generation observatories could constrain this initial mass function or help astrophysics actually figure that out?
There is a work by, once again, NG et al., also Salvatore Vitale. I have the presentation in the other computer. I might bring it up as we speak. It turns out that in order to determine the mass function at very high redshift is going to be difficult. If up to redshift of something like 3 or 4, it is pretty well determined. But there is one essential difference between what might happen with population 3 stars and primordial black holes. The population 3 stars are essentially gone by something like redshift of 20, hardly anything at all. Whereas primordial black hole binary mergers are still increasing at that time. Maybe I should go back to my slides and show, I think I had a plot. Yeah, let me just go back. So if you look at this top plot, I think you're asking how well can we measure this pink curve, population 3. If there are these primordial black holes, then of course it's going to be difficult. But even this is probably within a factor of about 5 to 10 at that redshift, if this is absent. There is a curve that is showing what is the confidence with which we can measure that, assuming this to be the case, and I can bring it up, but we can go on to next section as I try to bring up those slides.
So is that the merger rate though, or the mass distribution? Because I think the question was if
the merger density expected. I mean, all we can see will be the merger density, and that is proportional to the initial mass function, I guess. Is that not what you expect? That the merger density itself will be proportional to the initial mass function, right?
Yeah, well, I guess I was thinking about like if you can get constraints on the masses of the merging black holes, and you can model it backwards to see what initial mass function should be behind that merger, that masses of the mergers, perhaps.
Yeah, I'm going to connect. Sorry, maybe I don't have to connect. I'll bring up another slide in just a minute, and it is actually pretty impressive. Good. Okay, let me just translate what they found. Up to about redshift of 6, you can distinguish between different models and measure what you expect based on the star formation rate. However, beyond about redshift of 8, it's all mixed up. It's very difficult to determine the different models for these population 3 stars and so on.
Yes, Satya, just to follow up on that, I guess another problem for that is the redshift measurement, as you just show in this plot, that is just not good. So yeah, the mass, you can measure it, but with very large uncertainty. So if you try to reconstruct the mass distribution, it's not gonna be very accurate.
Absolutely. Basically, our measurement of intrinsic masses will be limited by cosmology. It's not really, in the sense, the measurement of the distance itself, because the masses are degenerate with the redshift.
Let me just see if there are any questions from Zoom. I don't see any more questions, discussion from the audience. Yeah, Javier.
I wonder if you could say a few more words about the design choices for the Cosmic Explorer. So you mentioned this thing, there are 2, 40 and 20 kilometers. Why?
Why? Okay. It turns out that I think Phil Landry, if he's here, He might be able to show a slide or two on that. What happens is, if you want to have good sensitivity, I didn't really put any sensitivity curve in my talk, I'm afraid. But it turns out, if you want to have good sensitivity beyond about 1 kilohertz, you can tune by sacrificing sensitivity in the hundreds of hertz region. Why do we want to do that? This is really to focus the sensitivity for better observation of neutron star mergers. You can tune a 20-kilometer detector to observe binary neutron star merger signals, post-merger signals, much better than the 40-kilometer detector. So the option would be to have both 20 and 40, but observing in the wideband sensitivity for a few years until there is need to, or even right from the beginning, if there is need to observe at the higher frequencies, this merger part of the signal, one can tune by just replacing a mirror, you will be able to observe much better at higher frequencies. This, unfortunately, is not possible for a 40-kilometer detector because it occurs, the second minima occurs at a slightly lower frequency, and therefore the tuning up to kilohertz, several kilohertz, which will earn you better neutron star merger sensitivity, is not possible. So that's the reason for one being 20 kilometers and the other being 40 kilometers. But we are going in for 2 cosmic explorer detectors in case you want to have a science case that is built only on cosmic explorer. You cannot rely on, let's say, a third gravitational wave observatory that is available. If you look at our trade study, you will see that 2 cosmic explorer detectors with 1 LIGO Voyager sensitivity will be able to accomplish most of the science goals. We have made a detailed comparison in the Horizon study document, how just 1 cosmic explorer, 2 cosmic explorers, and then all 3 observatories available. What are the different science goals that you can observe? I might very quickly bring up a box that exists there. Give me 1 second. I should have been prepared for this. Here it is. Oh, I need to switch my. Yeah, I won't describe it, but I'll just point you where you can find this information, namely the choices that we have made and how the different sciences can be accomplished with different combination of detectors. So you can find it in the Horizon study.
Thanks.
I think unless there's one last quick question, we'll need to move on at this point. So let's thank Sathya again for that great talk. Thank you, Sathya.